In my last lecture, we learned how to set up and evaluate the integral to find the rotational inertia for symmetrical distributions of matter as they rotated about an axis. We took a look at the one-dimensional stick, we also did the hoop, and we also did the disk. With a little bit of practice, setting up and evaluating the integral that is necessary to find the rotational inertias in those situations is relatively easy to do. Okay, let's take a look at a hoop once again. I have it right here as a demonstration tool. Recall what I did in the previous video. I rotated the hoop like so, about an axis that was perpendicular to the plane of the hoop, and the axis itself was passing through the center of mass. It's a relatively easy integral to set up. Imagine, however, now doing the following. Taking the axis, which was originally passing through the center of mass, and then moving it to the side of the hoop, that is, say, like so. This new axis here is parallel to the old axis, but now imagine that the hoop is rotating about this point here, that is, say, something like this. Setting up and evaluating this integral to find the rotational inertia for such a situation is rather difficult to do. However, there is an elegant theorem that we can use. A theorem that if we already know what the rotational inertia is about an axis passing through the center of mass, and then we move the axis to a new location, but it's still parallel to the old axis. This elegant theorem that we can use is referred to as parallel axis theorem. Let me go ahead and derive it here, and then we'll use it for a couple of simple situations. Okay, so first of all, let me go ahead and draw a coordinate system like so, and then let's say that we have an object here like this, and then by definition, let's say that the center of mass of this object is here at the origin. And then we could rotate this thing about the center of mass, that is about an axis that is perpendicular to the board like so. And then like we did for the hoop and the disk and so on, we could ultimately set up and evaluate an integral to find that rotational inertia. So let's say we already know what that rotational inertia is referred to as ICM. So we know ICM ahead of time. But now what we'll do is we'll take that old axis like so and then move it to a new location such that it's still parallel to the old axis. So this will be a new axis about which we rotate the object. This new axis, however, is still parallel to the old, hence the name parallel axis theorem. So right here is that new axis like so. We'll refer to this as A, and it's some distance here away from the center of mass, the old axis. This distance is usually referred to as H. Okay, now using the point mass notation, it's not necessary to set up an integral here. Using the point mass notation, what I'm going to do is just calculate the rotational inertia of this thing as it rotates about the axis that is passing through this point. So in order to do that, I have to have right here, for example, a little m sub I, like so. And then what I'm going to have to do is sum m sub I multiplied by this distance squared to find the rotational inertia about this new axis. So let me go ahead and set up that calculation. All right, in order to do so, however, I need to know coordinates, or coordinates, for example, are components of position vectors associated with the points here on this diagram. Now I'm not going to draw the vectors themselves, but let's say that this point here, m sub I, has an x coordinate like so, x sub I, and a y coordinate like this, y sub I. Like so. We're also going to need that for the axis as well. It has an x coordinate that we're going to call x sub A, and then right here is a y coordinate which we'll call y sub A. Like so. And now what I'm going to do is set up a summation of mr squared, where the r is this distance here. We'll use distance formula with these coordinates here from geometry, for example, to find this distance and square it. This will then ultimately start to give me the following for the rotational inertia about this new axis. Okay, so as I said, using summation symbols here, that's perfectly fine. I need mr squared. Okay, now putting it in large brackets, let's use distance formula and square it. So what I'm going to do is take the difference between the x coordinates and square that, like so, and then add to that the difference between the y coordinates and square that. Like so. And then we don't take the square root of the whole thing, we just take it squared like so, and this then gives us this quantity here. This is the distance squared between these 2 points. Okay, now let's just FOIL out each of these terms, multiply each of these terms by this summation, and then let's just see what happens as we do. All right, so to do so, I'll do it all here on the lower board. I need to give myself some room here. So let's now go ahead and FOIL this thing out. All right, so first of all, I have x sub I squared, like so. And then x sub I multiplied by negative x sub a, but there's two of them, like so. And then plus x sub a squared. Okay, and then do the same thing with the y coordinates here, so y sub I squared. And then let's see, minus 2y sub a, y sub I. And then lastly, plus y sub a squared. Okay, now I kind of end up with this huge mess, and then we have to interpret what I have. Well, what I'm going to do is start grouping some terms together. Okay, let's first of all group these two terms here with the summation symbol. Like so. Okay, now with the summation symbol, let's take this term here. I'm going to write it like this. So, okay, let's do the same thing with this term here with the summation symbol. I'll write it like this. Like that. And then lastly, this term here and this term here grouped together with the summation symbol. Like so. Like that. Okay, and now what's what? Well, let's actually take a look at these two terms here and here. Specifically in terms of the x direction, this term here. What does that look like? It looks like the numerator when calculating the position of the center of mass. Recall that the position of the center of mass for a system of point masses arranged along a number line, say the x direction, is all of the m times x's added together, and then ultimately you divide by the sum of the masses in order to find the position of the center of mass. That's the numerator of that term. So this right here is describing the position of the center of mass. Well, look at the diagram on the top board. What is the position of the center of mass in the x direction by definition? It's 0 because the center of mass is at the origin. So this term here is 0. Same thing with this term here. This is describing the y coordinate of the center of mass's position. That's the numerator, that is, of that expression. That's ultimately, once again, 0 because the center of mass is at the origin. All right, so these two terms completely drop out for that reason. Okay, and then what are we left with? Well, we're left with the following. Okay, first of all, take a look at this quantity right here. Notice that this quantity right here is describing an mr squared. This right here is an r squared, but it's specifically on the diagram above, this distance right here squared. In other words, this quantity here we already know. It's ICM. And then lastly, we've got this quantity here. This quantity here also looks like an m multiplied by a distance squared. However, on the diagram above, what is this distance here squared? Well, it's this distance h squared, like so. And the sum of the masses is just overall the mass of the object m. And we end up with this simple expression. This right here is referred to as parallel axis theorem. So as you can see, deriving it's a little tricky, but using it is actually really easy. So let's go ahead and take a look at two specific examples of the use of parallel axis theorem. I'm going to go ahead and erase the board in order to do so. Okay, so the first of those examples we have actually already seen from the previous video. It's a one-dimensional stick situation. So it says now, and please write it down in your notes, use the parallel axis theorem to derive the rotational inertia for the following. Part A, a uniform one-dimensional stick with mass m and length L with the axis of rotation passing through one of the ends. So here's then what we're asked to do in part A of the problem. Okay, here's the one-dimensional stick. It has mass m and length L. And then right here we'll say is the axis of rotation. So it's rotating like this. Okay, here's then how we apply parallel axis theorem. So I equals ICM plus mh squared. This was a calculation that we did in the previous video, which has to do with finding rotational inertia of the stick about an axis that is passing through the center of mass. It was the first integral that I set up. In order to do that, we then rotated the stick like this. This quantity was 1/12 ml squared. Okay, and then we add that to the following. The distance h now specifically goes from the center of mass right here to the position of the new axis. That's the distance h on the diagram, which is 1/2 the length of the stick. So now I have plus mh squared, so plus ml squared over 4. And now let's go ahead and get a common denominator here and add the two quantities together. So this right here is 1/12, this right here is 3/12 when you do the math, and then ultimately if you add them together you get 4/12. 4/12 is 1/3. You end up with 1/3 ml squared. So this was one of the derivations that we did in the previous lecture as well from the brute force integral. But if you already know this quantity here, finding this term here using parallel axis theorem is easy to do. Okay, let's take a look at part B, which has to do with my hoop situation that I used as a demonstration tool a little while ago. Okay, so the hoop problem is as follows. Okay, a hoop of mass m and radius capital R with an axis of rotation passing through the edge of the hoop perpendicular to the plane of the hoop. So once again, it's taking the old axis like so, passing through the center of mass, and then moving it to the side right here. Such that we're now going to find the rotational inertia like this. Okay, let me draw this out here for part B. Okay, so here's our hoop, like so, of mass m and radius capital R. Okay, right here is the center of mass, and then the old axis, like so, passing through the center of mass. We then set up and evaluated that integral that gave us ICM. Okay, ICM for that situation involving the hoop was mr squared, not the disk, the hoop. The hoop was mr squared. Okay, now what we're going to do is we're going to take the original axis and then move it to here. So right here is the new axis, like so. This then is the distance h in the expression, which is just equal to the radius of the hoop. Okay, now right here is parallel axis theorem. And then let's just plug in. So mr squared from the integral from previously, plus m times h squared, where h is equal to r. Add it up to mr squared. Nothing more than that. So that's a brief look at parallel axis theorem.